Okay, hi everyone. Thank you very much for coming. My name is Rui. I'm also a master's student at Alex. And we're talking about something slightly different, which is efficient top-K query processing on distributed column family databases. So we can start basically by discussing what is a top-K query. Well, very simply, it's just a type of query where we're trying to find all K objects with the highest aggregate score over function f. Usually that function is a summation function, and we see top-K queries everywhere. We see them in text search engines where we try to find top-K ranking entries in the search engine, or for instance, in time series data. In this case, it will be an analytics application where we're trying to find what are the months which are the highest visits for every month, for instance. In this application, in our implementation, we try to implement real-time top-K queries over distributed data sources, mainly because that's going to be integrated in a larger real-time analytics platform. Also, top-K queries are useful because we're not interested in the totality of the data corpus usually. Only the highest scoring pairs are useful for some types of statistical analysis. And obviously, from an efficiency point of view, we want to minimize our memory consumption, our bandwidth consumption, data transfer, and our computational cycles. So what do you mean by real-time? In this case, we mean obviously user real-time, not software real-time. So we're talking about a time period that spans between 100 milliseconds to tops probably 1 second. And there are several solutions to tackle the top-K query problem. I mean, the most simplistic one will obviously be the naive method, in which we have data sources. We just have a query coordinator. We take all the data from all the data sources. We merge all the data. We aggregate all the scores. We sort all the aggregate data, and then we select the KIs. Well, this is obviously not a good solution. For large amounts of data, it will never work. It will possibly never fit in memory. The execution time will not be real time, most definitely. And it's not efficient because we're processing pairs which we're never going to be interested in anyway. And obviously, for all the reasons above, it's not scalable. There are widely adopted solutions for top-K queries in batch operations scenarios, such as Hadoop and MapReduce, for instance. They are proven solutions, widely adopted. They're excellent for report-style use cases. Workers still have to process irrelevant information, and it has a downside in our scenario, which is not being real-time. To tackle this problem, there's been lots of research pioneered by Fagans, which created a threshold family of algorithms, which basically try to determine a threshold below which, no object can be a part of a top-K. The original threshold algorithm, however, had some shortcomings. For instance, it was not designed to work with distributed data sources. It is highly dependent on the distribution of data source, so it depends if you're dealing with highly skewed data, lowly skewed data. And most importantly of all, perhaps, is that it's not deterministic in terms of latency, because it's unbounded in terms of round trips. It keeps reading from the data source until it's satisfied it's found a threshold. So we cannot say for sure that our latency will be bound to a certain level. So we decided not to use threshold algorithm, of course. Our scenario is very different from the scenarios in which previous algorithms were used. They were mainly research for peer-to-peer networks. So in peer-to-peer networks, we have some characteristics. For instance, the peers are distributed solely physical, probably. Nodes in a peer-to-peer network might have the ability of execute arbitrarily complex code. So the node itself might execute parts of the algorithm. In our case, our nodes are database nodes, so they have a very limited processing capability. And obviously, we wanted to adapt the algorithms to the data access patterns and models of the chosen database, which was Cassandra in this case. So the chosen algorithms in the end were 3 algorithms, 2 exact algorithms, which means the average recall is 100%. They're always going to give us the exact top K results. They're built from scratch to be distributed, and they're fixed round trip, which means they have a fixed amount of round trips to the data sources before they terminate. And we also implemented and tested one algorithm called KLEE, which, apart from being also distributed and having a fixed round trip, it has the difference of being an approximate algorithm. So it gives us approximate answers to the top K query search. So this is just going to be a very quick overview of the algorithms. By definition, describing an algorithm might be repetitive, so I'm not going to bore you with that. So for instance, TPUT on the first phase requests all the top K objects from all the peers. It calculates the partial sum of all the objects in all the peers. It selects a case score as a threshold. In phase 2, it requests all the objects from all the peers in which the score is higher than the normalized threshold. It then recalculates the partial sum of all the objects and selects that case score as a new threshold. All the objects from all the peers which are above that threshold are requested. We recalculate 2 partial sums, a worst score in which missing scores are 0, and a best score in which missing scores are replaced by the normalized threshold. Objects whose best score is higher than the worst score are the candidates. And then in the final phase, we request all the candidates from the peers, we aggregate the scores, and that's our top K. So every threshold, the first phase is very similar to TPUT. The objective is just to get the normalized threshold. In phase 2, it sends to each peer all the candidates it's seen so far, their IDs and the threshold. It determines locally the lowest scoring pair from all the candidates seen in each peer. And then it asks for all the objects whose score is above the maximum between the lowest score from the previous candidates and the threshold. Again, last phase, it just recalculates the partial sum and names it threshold 2. And for each peer where the local threshold of the peer is less than the normalized threshold, fetch all objects, otherwise keep the objects it has, recalculates the partial sum, designates the case score as a new threshold. Again, recalculate the partial sum, replace all missing scores with that value, and the candidates are objects which partial sum are higher than the third threshold, fetch individual candidates. So you can see it's a quite complex algorithm, but the difference between TPUT is that it calculates local thresholds. So instead of calculating a uniform threshold for all the peers, it actually adapts the threshold to the distribution in each peer. So the final algorithm we implemented, just quick overview, is KLEE. It's a TPUT variant. The main difference is that it does a trade-off between accuracy and bandwidth. And to do so, it relies on summary data, on statistical metadata. So it asks for pre-computed data that gives a snapshot of the peer. And from that data, it can better estimate a mean K threshold without having to do an extra round trip. And it relies on 2 fundamental data structures to that metadata, which are histograms and Bloom filters. So an histogram for each peer would be just simply the number of candidates for, this is an accurate histogram. We arbitrarily determine the number of cells. In this case, we determined 100. And for each cell, it determines the frequency of the items on that cell, an upper bound and a lower bound, so the highest scoring, the lowest scoring item on each cell, and also average value for each cell. Bloom filters is the second data structure that KLEE utilizes. So they're a very space efficient and very fast way of testing set membership. The way it works is we have basically an initial bit set to zeros, and when we add an object, we actually apply, depending on the implementation, we apply a series of hash functions which will flip the bits on the bit set. If you want to test for membership, we just apply the same hash functions to an object, and if all the bits are flipped, it means it's probably in the set. If they're not, it's not in the set. So it's a data structure that can never give you false positives, false negatives, but it can give you false positives. In this case, we use an already implemented Bloom filter. We can implement from scratch. And obviously, this is very important. It's not isomorphic, which means just from the bit sets, we cannot know which objects are in there. KLEE has 4 or optionally 3 steps. It has an exploration step, so it asks for the statistical metadata and the top K objects. It has an optimization step in which decides whether to execute step 3 or go straight to step 4. In step 3, if it executes, it filters the high-scoring candidates, and in step 4, it retrieves the candidates from the peers. Now, the way it fetches the histogram data is it actually fetches a configurable amount of top-end cells, C, which we can define in our implementation, and it actually just requests for the average and frequency of the remaining low-end cells. The way it does the partial sum is iterate over all the objects seen so far, and if the object is present in a peer, it just uses its scoring in the partial sum, and if the object is not present in that peer, it searches all the Bloom filters for membership. If there's one match, it will use the average value of that cell it received. And if there's no match at all, then it just uses the weighted average of all the low-end cells in the estimation of the mean K. We now take the K value of this aggregated score, call it mean K, and then we can filter objects which are lower than mean Km from our candidate list. Phase 2 is a phase which we didn't implement, simply because phase 2 requires complex computations from the side of the node, which would be fine on a peer-to-peer network, but on a database node with limitation computation capabilities such as Cassandra, it will be difficult to do. So basically, it would request a bit set of all the objects scoring higher than the normalized threshold, and then back on the query coordinator, it will do a statistical pruning, leaving just the most common objects on the candidates list. And obviously, this step was not implemented, but we'll look at a way in which it's possible to implement it on the future work. Phase 3 requests all the candidates from the peers. It performs a partial sum, such as all the other algorithms, and selects the KIS objects as our top K. So this is just an overview of the algorithms we implemented, and the backend in which we decided to implement it was in Cassandra. So Cassandra is a fully decentralized column family store. It's widely used in analytics due to its famous scalability. It's almost linear scalability. It has no single point of failure, so there are no master or slave nodes. It performs automatic replication, and also, as it is decentralized, clients can read or write to any node on the cluster, and Cassandra automatically takes over any duty of reorienting answers, or in case of writes, redistributing the database into a consistent state. So one important thing about Cassandra is the way in which rows are located, because that will influence directly our implementation. Cassandra performs automatic partitioning of data, and the most commonly used partitioning strategy is a random strategy. In this strategy, rows, as we can see in that table, have a primary key, have several primary keys, but the first primary key is called the partition key. And the hash of that partition key in pink will determine in which node the row will be. And the crucial thing to remember in Cassandra is that each row will be physically co-located in one single node. So even though we might have a table which is partitioned all over the nodes, each single row will definitely be located in a single disk or in a single node. So the data model for Cassandra works in a way in which primary keys also have comparators. So columns in the same row are physically collocated, as we've seen, but we can look at these two different tables, for instance, and the main difference is on the table on the top, the comparator is ID. So all the columns in this row will be ordered by ID, and they'll be they'll be ordered physically on disk, which means that if this was another ID, say ID 010, and then inserted ID 02, it will be physically inserted between ID 01 and 010. In this case, it is obviously the same logic, but we're ordering by score. This is important because it makes range searches extremely fast in Cassandra. So they're usually just a linear seek on disk. So doing something like give me, for this row, all the columns which have a score higher than this will be extremely fast. Cassandra's model language, a data model language, is TQL, which is very similar to SQL at the first view. So, for instance, the first two statements are CQL, but it could be SQL statements. They have, however, limitations. Cassandra does not support joins, does not support unions or subselects. It does not support aggregation functions, so minimum or maximum functions. They are not available. And inequality searches are bound by the primary key declaration. That will be explained on the next slide. Basically what it means is, if we assume, for instance, this table, in which we have two primary keys, the first two statements we see there will be valid SQL statements. However, they're not valid CQL statements, because to be able to use an inequality on user ID, we'll have to have a fixed value for date. So we could only do, in this case, this type of search and not do use inequalities on any column for the database. This is quite important, and it leads to a design solution for our implementation, which will work in a second. So this is just an overview of how we implemented our top-K query framework. So basically, we have a query coordinator, which has a very simple interface with, or better, we have algorithms which implement a very simple interface, so we can just plug in any kind of interface algorithm we want, which is actually what we did to do all the testing. And then we have a peer interface whose implementation uses the asynchronous capabilities of the driver, of the Cassandra driver. So this is actually very good because we can actually start, if we have a huge amount of peers, we can actually spread out a huge amount of asynchronous calls to the driver. And then we can just do the synchronization with a small thread pool on the query coordinator. And it's obviously very handy to deal with lots of numbers of peers. So this is a challenging I was talking about when I said we have to be mindful of the primary key or the schema of the table when we do searches on Cassandra, because the algorithms at some points they require candidates, so they require IDs, and at some points they require objects which are above a certain score. So to do that, the only possible way of doing that in Cassandra, in this case, or the simple way of doing Cassandra, was to implement forward and reverse tables. So we have exactly the same data, but in one table we have a comparator as ID, so we have a primary key on ID, and on the other table we have a primary key on score. This is not a problem because space is cheap. Cassandra uses built-in compression, which makes it even cheaper, I guess. And denormalized data obviously compresses very well. And we always have the advantage, for instance, in the parts of the algorithms where we have to ask for pairs above a certain threshold, all the columns are pre-ordered at the database level, so we don't have to worry about that. So there were some challenges, obviously, to implement these top-K algorithms. One of them is decompose the tasks. Some tasks in the algorithms, such as, for instance, in the average threshold, are one single step, As you can see, we send the list of candidates and the threshold value, and then the peer determines the lowest scoring and selects the objects above the maximum of the threshold and lowest scoring. We had to decompose this in our implementation, obviously, because Cassandra nodes could not perform that kind of operations. So we just have to first send the whole list of candidates. We retrieve the list of candidates. We calculate the query coordinator, the maximum. Then we fetch the objects which are above that maximum. So here we just have like a very simple overview of how we might implement TPUT. We just, for instance, fetch the top K objects from the inverse table. We perform the partial sum. After we have a partial sum, we have a threshold. Then after we calculate the final threshold, we just ask for all the objects from the inverse table, which are above a certain score. It's a very fast operation. And finally, once we have the K value and we can determine the K hat, the candidates, we just determine individually. We fetch them from the forward table. Cassandra can support in statements, so you can just fetch values which are in the array of candidates. If you notice, I mean, one thing which is interesting is in relational databases, if you wanted to fetch candidates from several rows, we could just do we can just ask for the candidates across all rows. But that would be an anti-pattern in databases such as Cassandra distributed databases, because each of one of these peers might be on a different node. So it would make no sense in terms of performance or data model for Cassandra. So this is just quickly to show hybrid threshold is the same rationale. I mean, the peers ask from the forward or inverse tables the values they need. This is just repetition of the algorithm. We then use accumulator and synchronization on the query coordinator. Another challenge we notice is that, as I mentioned, sequential lookups are very fast. Random lookups are much slower. For instance, in this case, for the exact same number of objects, you can see the difference of time as 100-fold difference of time of fetching candidates. And as such, I've implemented just a quick modification to KLEE on top of KLEE 3, in which, to avoid fetching a large number of candidates in the final phase, we basically, instead of filtering candidates with a score lower than min K over the number of peers, we just do a range scan per peer with a score higher than min K over n. So this has a trade-off of a higher data transfer versus a smaller execution time, and we'll see that on the experimental results. So this is how we basically mapped the statistical metadata to the Cassandra schema. So basically, for each peer, we had a certain number of cells. We just mapped the frequencies, the lower bounds, upper bounds, the average values, and the filter was serialized. The boom filter was serialized as a binary and stored as a blob in the database. And then at retrieval time, it's deserialized into a boom filter again. So basically, this is a process. We can, when we create the statistical metadata, we can configure the number of views we want, so we have a better trade-off between space and probably accuracy. We can configure the maximum false positive ratio for the boom filters. And the way it's created is basically the histogram creator class just fetches all the rows, determines the maximum score, creates n bins, partitions the objects per bins, and populates the boom filters, serializes everything, and saves to the row. So basically, this is just a schematic of how KLEE works. So basically, you have on top the first step of asking the top K values. Then you have the second step, asking the full metadata values for a certain number of cells. Then you ask for the remaining average and frequency values for the last cells. And then we just do the processes of getting the candidates as in the other algorithms. So the histogram creation API is quite simple. Basically, you just instantiate the histogram creator with a table definition. We can specify max positive false positive ratios, and then we just give the set of keys, which can be any kind of object, and it's created automatically. Now, one key question, sorry, this slide is out of order. For synchronous communication, we did extensive use of listenable features. This was very good because it allows for highly concurrent access to the database with a small thread pool, and actually because it actually allowed us to decouple the peer implementation from the query coordinator and the algorithms. For instance, we can do lazy transformation. So once we fetch the data from Cassandra, we can actually do a lazy transformation of a result set or future result set into a POJO, and this will be returned to the query coordinator as a future POJO, so we don't have to handle directly with result sets or any of that in our query coordinators or algorithms. So the API to actually do the top K queries is try to be as simple as possible. We basically just create a JSON file with the general overview of the tables we're interested in. So it doesn't even have to have all the columns you want. It just has to have 3 main columns, which is which column is the score, which score is the object ID, and which defines the peer. And then we just instantiate the query coordinator with any type of algorithm we've implemented or any future algorithm we want. We set the keys. In this case, we want to find the top K visits, which is they will define by IP address for all the days between the 1st of May to 26th of July. We just say get top 10 and get top 10, and we get the top K value. So the datasets in which we actually implemented this and tested these algorithms were 2. One of them is the Zipf distribution, which basically is just a score distribution with a configurable skewness. It's usually used in the scientific literature as a good approximation as real-world data, but we'll see that probably in some situations it's not. And we also used kind of standard real-world test data, which is the 1998 World Cup data. It's available for download in the common log format. The IP addresses have been anonymized. It has around 1.4 billion entries and 2 million unique visitors. It goes from 1st of May to 26th of July. It is a highly skewed data, as you can see here by the calculated skewness, and also with varying numbers of elements per day in this case. So the results, how do the algorithms behave with this kind of data? So you can see for the synthetic, I'm sorry, naive doesn't show on this one, but it's not the most important one. We can see that here we varied the K and tried to determine how the bandwidth or data transfer change with varying K. We can see that in the synthetic distribution, we have kind of stable variation of data transfer between the peers. This was done, by the way, for 100 peers with 10,000 elements for a synthetic table. We can see it's pretty much stable. For quiz modified, we can see, as we said, there's going to be a trade-off between data transfer and execution time, so it's a bit higher. But here with real-world data, we can see that average threshold, for instance, is all over the place. It's not behaving very nicely. However, TPUT and KLEE are almost flat in terms of increase of data. So we can see that the amount of data that we transfer with increasing K from, say, top 5 objects to top 100 objects is almost the same. Execution time with varying K, I mean, I just drawn a line here on the 1 second, which is a kind of arbitrary line to try to determine what is real time or not. We see that execution time for varying K, both in the synthetic and on the real world data, is pretty much flat for some algorithms, like KLEE M and TPUT KLEE3 in this case, and therefore KLEE3. And it's interesting because this can open up some practical implementations. For instance, if we're interested in doing some kind of web application or any kind of service in which users want pagination, I mean, why bother giving them 20 results at a time? I mean, we can just fetch 100 results, it'll be real time, and then we can just cache them and give them the rest instantaneously. So we can see it behaves quite well with varying k in terms of execution time, these algorithms, except average threshold. Now with varying number of peers. So now we can see that, well, naive, of course, grows linearly with the data set, and KLEE3M also grows a lot, and all the other algorithms also grow, but they have a sustainable growth. 100 peers is quite a lot of peers for real-world scenarios. So say if we wanted to search for data for months, let's say for the top k of certain months, 100 peers would be 100 months. So that's a quite wide interval. So we can see it still behaves in a good fashion for a high number of peers. For real-world data, we see the same kind of good behavior for these algorithms, except average threshold, and obviously naive out of the question as it grows almost exponentially. Now, execution time for varying peers. This is a different type of result, obviously. We can see that for the test data that we had, we still managed to get real-time results, but we can see a trend in which they are growing linearly. So this will reach a point in which it's not scalable. So, I mean, if we add like twice more peers, it will probably not be real time anymore. But there is a way of going around that, as we'll see. So these are, for instance, just some example results. So this is doing a top K for all the days between the 1st of June and the 18th of June, trying to find the top 10 visitors for the World Cup data servers. And we can see the huge variations in terms of data compared to naive, which is baseline, the huge variations in terms of execution time. And as it is a highly skewed distribution, we can see that the accuracy is actually 100% for KLEE, which is by definition an approximate algorithm. So KLEE has one, it has one prerequisite, which is it can only be applied if there is statistical metadata. So the question is, if we're on a production situation, where say we want to use our real-time analytics platform, and we're planning on using KLEE and getting historical data every hour, if we're reaching the end of the hour, we want to use the algorithm as soon as the hour ends. So it's important to know how long does it take to generate the statistical metadata. I mean, if 1 hour ends, how long does it take? Does it take 2 hours to generate the metadata? Well, fortunately not. It's very, very fast. You can see it's a linear increase by the number of peers. And actually, for one peer with 100,000 elements, it takes 56 milliseconds to generate the statistical metadata. So it is feasible to do it on the fly. So to have some kind of trigger of as soon as one bucket or one period is finished, we can immediately calculate the statistical metadata to be able to use KLEE. So we're talking about the scalability issue with the increasing number of peers. And one of them can be with data denormalization and pre-aggregation, for instance. If we think that we can have rows of number of visits of IPs per day, we can also have aggregates by month, for instance. And in this case, the algorithm obviously is valid. I mean, applying the same algorithm, mix and matching dates and months, as long as they're exclusive, obviously, will produce the exact same results. So in this case, for instance, if you wanted to find which are the top 10 visitors from the first day of March to the second day of July. Instead of calculating it over 63 periods or 63 days, we can just use May, June, and then 2 days, and we'll calculate it over 4 periods. And then we have huge increase of, obviously, of data transfer and execution, huge savings, sorry, of data transfer and execution time with pre-aggregation. So we can see in this case, the difference in black we have doing a top K over 246 hours, and in red we have doing the same algorithm for 10 days and 6 hours. And the result is exactly the same, and we can expect savings over 96%, 90%, or 97%. So as our final evaluation, we can see that TPUT and average threshold are well-suited algorithms, not just as originally researched for peer-to-peer networks, but also for distributed databases. In some of the tests we did with real data, we saw typically savings of 98%, between 98 and 77% in execution time with no loss of precision, and in data transfer between 99.9% TPUT and 67% in average threshold. The advantage of TPUT and average threshold is obviously they do not need any kind of additional change to the infrastructure of the database. KLEE does need, obviously, the statistical metadata, but as we've seen, it's efficient to create, and we can even make it faster, discarding the final patch phase for less accurate results. But even so, with the version we've implemented, we saw savings of 99% in execution time and data transfer. So scalability is also can be addressed with good planning for data models. Average threshold probably didn't behave as well as expected because of low object correlation between the real-world data set, because the synthetic data set is constructed by a certain set of elements which are the same for all the peers. And that's not a real-world scenario, obviously. I mean, when we look at a log, some visitors go in one day, some visitors don't go in another one. So probably average threshold was less resilient to that low correlation of objects. But even though TPUT and KLEE were resilient to that, and with high K variations, we actually saw very stable results. So for future work, there is KLEE4, obviously, so the extra optimization step for KLEE4, which is possible to do using solutions like Introvert. So Introvert is an application server which is built on top of a Cassandra node. It's based on the Vertex application framework, and it actually allows a Java client to communicate with Cassandra via Introvert. So it's a middleware, kind of middleware for the database. And the main advantage is that along with the normal queries for a database, it allows passing arbitrary codes in several JVM languages, such as Groovy or Clojure, which are executed at the server side and can be used to transform the data before you get it back. So using Introvert, it is possible to actually implement the task of creating a bit set or a hash array to pass back to do the filtering step on KLEE4. This is not concluded, but TPUT and average threshold have already been implemented using Introvert in this work. But KLEE4 is still in progress. So I would like to thank you, Jonathan Halliday. It was extremely helpful with technical expertise, supervision, and support. And any questions?
You know, the captions were small.
It was crammed and too long.
Then you like me to talk in your talk, you start off like
Okay.
this.
Someone has to poke me.
I felt you could have done with a bit more of a concrete example at the beginning about what a top K solution is. You know, I've got a vague idea of what it is, but you know, you've got the World Cup data set in halfway through, or 3/4 of the way through.
Right.
And I mean, the slide at the beginning saying,
right.
this is a question we would ask about a World Cup data set. This is the sort of thing that a top K query is. You know, certainly would help me who's not doing that thing on a day-to-day basis. And I don't know what your audience is going to be, but assuming they don't really know what a top K query is, just giving a real-world concrete example to start, and then keep tying it in as you go along. Certainly with some of the examples of the questions you're asking and where you've got graphs, that would help to.
So I didn't know what top K was before today, and when you gave the first slides, I kind of had a bit of an idea, but then I understand now, and I don't think it's that complicated, but I didn't really get it from the first slides. I don't know. It took me a while to. I was already quite a way in before I kind of figured out what it was, which kind of meant that the first few slides I'd lost.
I assume that.
Yeah, I think maybe I can see why you assume that, because it's kind of something that people use every day, but you don't necessarily realize you're using it. Yeah, exactly. Yeah, so maybe even just like, because you used Google, didn't you, as an example?
Yeah.
I think because you typed top K into your search engine, it wasn't clear whether. I think if you typed something else like football or something, to be clear as an example, it wasn't obvious that you were using top K as just some random string that you picked. Yeah, but I think what I'm saying, it took me a while to understand what top K was, which meant you'd lost me on the first few slides, and I found it difficult to get back on board. You know, after I was struggling to keep up because I didn't understand what top K was, and I think there was a lot of content. And not having a background in it, I was finding it very difficult to, keep. I know it's not a very constructive thing to say, because I'm not sure exactly. I'm not sure what you can. I think, as you say, you can spend more time on the top K at the start.
That might be just less
The question you're going to ask the data and the answer you get.
Yeah, I think the Google one's a good example, because you could say you may not have heard of top K before, but you use it every day. Every time you go to Google, you use it, and you're probably using it in other places that you don't realise.
I'm not entirely sure. Whilst Google is an example of you using it, I'm not sure it's very concrete, because the questions that Google asks are very, you can't really put them down into a concrete thing. Whereas, the top 10 visitors to a site, it's easy. The top 10 IP addresses is very easy for someone to understand, whereas Google's, this is the top 10 websites for this particular query, is like, well...
It's quite woolly, isn't it? We don't know how Google's... Yeah. And that, they don't necessarily want us to know either. No. Their algorithm. No. Yeah, that's a good point.
A simple, if you're asking a simple question, it's easy to sort of think how you get more complex, but if you've got the simple thing in your mind, it's easier to plan things to real-world things. And,
Yes. I think I was just trying to think of something that everybody would be able to connect with.
Yeah.
But I guess you can, if you wanted to know, the top 10 scorers of all World Cups or something, you could.
I thought there was a lot of good material in there. I didn't know what top K was, but looking at the pacing, I thought once you launched into the three different kinds of algorithms, places in them, I think a few of those, because you're familiar with it, you'd have just maybe glossed over it a little bit too quick for people to take in.
Yes.
So, so I could follow you for 2 stages, and then you were on to the next algorithm before we quite got our head around the other bit.
I didn't realise there were separate algorithms for the last slides.
Right.
I thought it was just part of the same.
I think my main concern was the timing. Because
Every 10 minutes over.
Yeah, I mean, obviously something has to cut somewhere. And so I mean, I was trying to explain them as quickly as possible, not because I wanted to get them out of the way, just because I was worried about the time.
The problems which you were trying to solve that flow from those are dependent on how those algorithms do work because of the network traffic or the...
Sorry to try to summarize.
Yeah.
I think one thing you could probably do and print out a third of your things is a lot of those graphs where it shows the scaling. I'm not really sure you need to show them in your presentation. You might show one or two of them, one of them, and then say, here's a summary table which says, KLEE 3, just say it scales linearly up to, or, just summarize it in the table where you can get 10 graphs on one page, rather than just clicking through the graphs and people are thinking, what does that mean?
Yeah. So, okay, I've added that note down for you. It wasn't clear to me, and I don't think it still is actually. Did you implement all of them? B, did you implement none of them? C, did you implement some of them and compare it to the others?
No, we implemented all of them.
You've implemented all of them? Okay. Maybe you said that and I just missed it, I'm not sure.
So the experimental results, all of this is actually the real run of the algorithm.
Okay. Sorry, when I said implement the algorithm, sorry, you haven't designed, are the other people's algorithms that they've come up with and published, and you've implemented them?
Yes.
Right, okay.
Sorry,
I used the wrong terms. So you've implemented them all, but you didn't invent any of them?
No.
Right, it's okay.
So these are the state-of-the-art algorithms.
Right, okay.
But, on the other hand, they've never been used before, as far as we know, they've never been used before in distributed databases.
Okay.
So they've been created to peer-to-peer networks, to do searches and peer.
So you're learning the characteristics of each of these state-of-the-art algorithms when applied to this scenario, which is the weather value. Yeah. So maybe, I don't know. Did you cover? I'm not sure if you covered that in the slide. I may have just missed it.
Probably in the first one. I said one of the main differences is that in a peer-to-peer network, you can delegate a huge chunk of the algorithm to the peer because it can execute arbitrary code. But in our situation, a node is a Cassandra node, which can only do a very limited amount of computations with CQL. So that obviously is going to shape the way we implement that.
Yes, I think what I'm saying is I don't know if you said in your slides kind of an overview of the elevator pitch. So I think your elevator pitch is that we took. Yes, we took 4 state-of-the-art algorithms for doing K-top, and they're not traditionally applied to the situation of distributed something. You can probably explain better than I can. And then we ran simulations, or we did whatever, to come up with, see what the characteristics of each algorithm were, so we could understand what the strengths and weaknesses were in different scenarios, so that we can essentially provide the reader with a sort of critique of which algorithms to use in which scenario. So that might sort of help at the start, just to give a. Because I think I would have understood if I had that at the start. I think I kind of would have understood what you were doing throughout. That makes sense. So I'll just put elevator pitch, and then we can, if you know what that is, yeah. And the other thing was that,
Can I suggest that if they're just internal ones?
Oh yeah, sure.